First thing we want to talk about today is the Doppler effect. The Doppler effect is when we have a change in frequency due to relative motion between two objects. So first let's start with our object that is making a sound. So if we're just standing still, we kind of get these nice even waves. Remember, the waves are traveling in this direction, okay, emanating from the source out that direction. So if you're just standing here, as the wave approaches you, you're going to hear, crest, trough, high pressure, low pressure, so on and so forth, at this regular rate that sound is traveling by your ear, and so you're going to hear that frequency. However, if while you're listening to this, you're moving towards the object, right, that's sort of artificially increased the velocity of the wave because the wave is moving this direction, you're moving that direction, so there's actually a higher relative velocity between you. So you're actually going to hit these wave crests at a faster rate than you normally would if you're just standing still, and so it's going to sound to you like there's a higher frequency. So if there's things moving towards each other, relatively speaking, in terms of relative velocity, you get a higher frequency. On the other hand, if you're moving away and the waves are moving the same direction as you, you're going to encounter these wave crests at a slower rate than you would if you were just standing still. And because you're going to encounter them at a slower rate, that's a lower frequency. So you're going to hear lower frequency as things move away. So the thing to remember with Doppler effect is as things move towards you, you get a higher frequency. As things move away from each other, you get a lower frequency. For example, when the car or the ambulance maybe runs and goes by you, it sounds high-pitched as it's coming towards you, low as it's moving away. That's a Doppler effect type of thing. So now we want to look at a case of sort of instruments, if you will, in producing sound called a closed pipe. So what we're thinking of is something like this, where we have a pipe. When we say closed, that just means closed at one end. Obviously, if it were closed at both, it wouldn't do a good job of creating sound. So the sound's going to be created in here. We're going to get certain resonant frequencies, certain natural frequencies in here based on the length of this tube. So length is going to be a big factor here. And then those sound waves can travel out of the tube and we can hear them. Two important things to remember. One, we're going to get a reflection off of this side of sound since there's a barrier there. This open end, where we have a difference between the air in the tube and out of the tube, can also act as a barrier. So we get sort of standing waves that will get set up in here like we talked about a couple of videos ago, when things had barriers on either end. So we'll get a standing wave that's set up in here, and that standing wave, just like it was on a string, will be affected by the length of the tube. So this picture maybe kind of shows it a little bit better than what I can draw. So here's our closed pipe, and because of the way the wave has to fit in here, there's only certain frequencies that can fit in here. Remember we talked a while ago about fundamentals and overtones or harmonics. The same sort of situation here, where I can only create a certain number of waves based on the sort of constraints here. These waves are showing the displacement of air. At the end, air can't really move anywhere. It's at a barrier, so there's a node there where displacement's occurring. However, we have to have our maximum amount of displacement, an antinode at the very end where it's encountering the regular air because it's going to move back and forth real easily there. So the longest wave that I can fit in there is if I have a node here and an antinode here. Well, that's only a quarter of one wavelength that fits in there. So if you were to calculate the frequency, it'd be velocity over 4L. The next possible wave that I can fit there to make sure that I have a node at one end and an antinode at another happens to be 3/4 of a wavelength. And I have two nodes and two antinodes, and we get a frequency of 3V over 4L. Continuing with the pattern, now I have 3 nodes, 3 antinodes for my next pipe here. Again, antinode at this end, node here, and I get 5V over 4L, and then 7V over 4L. So you'll notice each time we've increased this number from 1 to 3 to 5 to 7, so it's by odd numbers. Following this pattern, we can actually come up with a good equation here for our waves. And we can say that the frequency of any closed pipe is going to be NV over 4L, where N is going to be what we call our harmonic number, and it's going to be 1, 3, 5, so on and so forth. So it's only going to be odd numbers. That's a very important thing to know with closed pipes. Closed pipes are only odd harmonics. you cannot have an even harmonic in anything that is a closed pipe. Only odd harmonics are possible. So that affects, how your instrument sounds. When an instrument plays, it's actually playing, this is the one you hear loudest, most intense, but all of these other frequencies are blended into it at different intensities depending on the instrument. And so the sound you hear is actually kind of the combination of all of these. And since you can only produce odd harmonics, an instrument made out of a closed pipe will sound slightly different than an instrument, a similar instrument made out of an open pipe. So big key here is just follow the pattern, 1, 3, 5. So 1 would represent our fundamental, then our second harmonic, third harmonic, so on and so forth, or first overtone, second overtone, so on and so forth. And you just kind of follow the pattern based on what the problem's asking you. Now with an open pipe, instead of being closed at one end, it's going to be completely open at one end. And again, length is going to be a big factor here. And instead of having a node at one end, since it's open on both ends, we have to have an antinode at both ends. So our standing wave, maybe a possibility for a standing wave looks like that, where I have an antinode at each end. The first couple harmonics look something like this. So the lowest possible frequency or longest possible wavelength I can fit in this tube is going to be half of a wavelength. All right, so that's only half of a possible wavelength. So antinodes at each end, a node in the middle. And that would be, wavelength would be 2L, so a frequency of V over 2L. Next possible, I could have a wavelength, kind of exactly one wavelength, so that's V over L. Then I could have a wavelength and a half, so 2/3 L, or 3V over 2L for my frequency. Then I could have 2 wavelengths, so I'm kind of increasing by a half a wavelength every time. And so you can kind of see the pattern here is slightly different. First, instead of dividing by 4L, it's 2L because we're dealing in half wavelength from our fundamental rather than a quarter. And then we're increasing sort of by a factor of a half every time, so we're sort of adding a half every single time. So the equation for our whole series looks something like this. We're going to have NV over 2L, and this time we can produce all possible harmonics, so 1, 2, 3, so on and so forth. So we can have all possible harmonics with an open pipe. It's not like a closed pipe where it's limited to just the odd. And so by following this pattern, we can sort of see again the whole harmonic series that an instrument could possibly produce. Again, when an instrument's played, fundamental is the loudest, and then the other ones are blended in at various intensities, and that's what gives each instrument sort of its unique sound, is sort of the blending of all of these other overtones.